is a matrix, we can expand this ideas.
In an and is a to the power iota ht divided by h bar. This so this is a and this quantity what you call it as uh, now create this unitary operator that is or e to the power iota ht into various segments, and once you diagonalize this we can actually get the final state. So as I said, in quantum system any kind of things I want to do that I can actually uh, take it actually so once I diagonalize this solvable easily. When written here that when it and we get the corresponding unitary operators and we ended up getting the Qiskit. But so this there is nothing quantum computing here. There is nothing anything that is incorporate anything I have incorporated quantum computing I have incorporated. But what is the problem here is when it scales, when this Hamiltonian matrix scales, so the dimension of the Hamiltonian matrix when it scales up, it becomes very hard to manually calculate by hand. So if a quantum computer can somehow solve it, or if a quantum computer can exactly help me to do it, that would be a really good thing, because there will be some uh, usefulness of in terms of advantage. We can show the usefulness of quantum computers. Now, as I said, the problem here is where it becomes hard is when the dimension of the Hilbert space increases. It blows up for so for n qubits, the total number of the possible states, as we all know, the 2 to the power n. And when we want to simulate this, both time and memory explode very quickly. So this is the problem we will have or will face when the dimension of the Hilbert space as well as the Hamiltonian matrix increases by a lot. So we need to find some other ways, or maybe some ways that a quantum computer can solve it. Now these are the traditional uh, numerical methods that can help us to utilize this whole operator, that is our e to the power iota ht, which may look a very simple, crisp term, but it is not so much simple. Why? Because I've just explained in the previous slides that it's an infinite series, and it's not a very straightforward and a simple way to write it down and to calculate this. Uh, so these are some of the traditional methods. One is the trotterization product formulas. One is linear combination of unitary, which is the sum of unitaries, and another one is the truncated Taylor series. So, but in my slide, in my presentation, I'll be mostly speaking about the product formula, focusing on Suzuki trotter decomposition. Now there is one more problem. So as I said, I wanted to solve this equation, right? Why? Because it will help me to get the evolved state over a certain amount of time of a quantum system. What it will do for me? It will help me to calculate or simulate molecules over a certain amount of time. I will be able to know how a molecule will behave after a certain amount of time. That this equation, if I somehow able to solve this equation, I'll be able to do that. Now I can do it by hand, but just I said, the problem arises when the dimension of the Hamiltonian matrix increases by large. So there is one more problem, as I was saying, that H is a matrix and H cannot be consist of a single term. It can consist of multiple terms. 1, 2, 3, 4, you name it, 10,000, 50. Classically, doing it by your hand, almost impossible. One more thing, I think because exponential of the algebra of basically exponential of any number. So it nothing very complicated and nothing very it's a very straightforward way to do it. But when it becomes a matrix in quantum mechanics, we call it as an operator. We cannot do it. Why? Because if A and B does not commute with each other, that means A comma B, AB minus BA not equals to 0, we cannot write this, because if we comes along the way. So if this term equals to 0, then we will be able to see equals to this. In most of the cases, it does not commutes with each other. So A and B does not equals to this, which may be a very of things, which does not intuitively follow the traditional algebraic methods. Yeah. So as I said, I can create a circuit of this by each card. So how I can create this circuit from scratch without knowing any quantum computing, only by just knowing mathematics. All right. So this is the main idea that so I'll divide this whole operator into chunks, and I'll create so many chunks that wonder how do I know that this will be exactly power of, let's say, this is a, that's why you call it as an approximation method. So the main idea of tautorization is to break this whole unit and say 10 seconds or 20 seconds. So I'm breaking that whole thing into small chunks. The whole unitary operator I'll be breaking into small chunks, and I'll be creating the molecular Hamiltonian kind. it's very different that how we experience everything that is around you see around yourself. It's a 3D world. It has three dimension. But the challenging thing you could have easily imagined that how whatever you see around yourself, this 3D world, how you can encode this into a quantum computer so that a quantum computer can understand your problem. So a quantum computer does not what is 3D space, what is 4D space, or what is 2D space. So we have to somehow encode this whole Hamiltonian form in such a way that a quantum computer can actually understand. So this is the standard mapping. There are also a lot of procedures and mappings that are already available, and that are already there. But this is kind of the standard way to do it. So first we have the molecular Hamiltonian form. So I think how many of you have heard? All right. So where you have the two terms. So Hamiltonian basically, if you have a system, if you have, let's say you have a system, Hamiltonian is that quantity. You have a box. Imagine you have a box. Okay, enclosed six, like the dicey box. And inside that, there is a particle. So Hamiltonian in physics, Hamiltonian is that quantity which will include all the information that is available in that box. Like if you consider that box as a system, although it might be very crude to sound that as a quantum system, but if you consider that a quantum system, so a Hamiltonian is that quantity that will tell you each and everything about that system. So that's known as the Hamiltonian quantity. It includes two things. One is the kinetic energy and another one is the potential energy. So if you write down the, although it's a very, don't get intimidated by all of this equation, since you are mostly beginner, so I would like to highlight the fact that just try to get the idea about what exactly am I doing. You may not necessarily understand what all the detailed mathematics, but the Hamiltonian of a molecule, like let's say I have a H2O molecule, H2O, or let's say I have a CH4, or let's say I have some more complicated molecule. So the Hamiltonian will look, if I try to write it, as I said, Hamiltonian includes all the information of a quantum of a system. So it generally kind of takes a form like this, right? A mathematical form where these are the nuclear repulsion terms, and these are the electron repulsion term. These are the electron nuclear repulsion term. So all the information it is encoded here. Now a quantum computer will not understand, or it does not have any capability to understand this, how it is. So it's our responsibility to make the quantum computer or quantum algorithm understand that how this molecular Hamiltonian you can analyze. So to do that, we follow the standard procedure of from going from molecular Hamiltonian to second quantized form, which is this. Again, there's a lot of mathematics involved, but just get the flavor of it, that from how it is getting done. So where A dagger Q is a creation operator, and AP is the annihilation operator. Now, from the second quantized, which is the fermionic form of the Hamiltonian, we get to the qubit form. Now, this once we using mapping, we ended up getting the Hamiltonian operators equivalent form that a quantum computer can actually handle, which is nothing but in this form. So you see, I have applied some kind of the logic or some kind of way of thinking, so that my from this molecular Hamiltonian, I came to this qubit Hamiltonian without losing any information. So that is a very challenging thing. So once you have the qubit Hamiltonian, that means I have, let's say I have a H2O molecule. Now, if I do all of these operations and stuff, I'll ended up having a Hamiltonian that has all the information of that H2O molecule, such that a quantum computer can actually handle. Now, for example, I have tried to showcase here how a 3-qubit Hamiltonian will look like. So here, this is the Hamiltonian term. And Yeah, it's a very I is the identity operator and Z is the Z get basically. So what? All right. So as I said, my operator just to break this into multiple slice. Just so I have started off with my Hamiltonian of this. So so just get the flavor of it. That I'm not formation of my H2 molecule into this Hamiltonian, but I have taken some example of it. Now both order one. What exactly will I get is so as I said, now my unitary operator that yeah. So my why I think I already highlighted that fact, but my main motive was to create how to solve this equation using a quantum computer, and to do that, I needed some HT. Now, yeah, the e to the power iota HT. If I just replace this H into this, I'll be getting this for a Choosian time and a reasonable decomposition strategy. So I think these are the matrices all of your all these gates X, Y, Z are nothing but these matrices. Similarly, Rx, Ry, Rz, that whatever you see in all Rx, Ry, Rz, if you just see the mathematics behind uh, how exactly the matrix of it looks like, so it exactly looks in this form. Okay. And if you just apply R pi by 2 or X pi or I pi by 2, so what I'll do is I'll X as Ry minus pi by 2 Z Ry plus pi by 2, and I can use this properties. And if I just replace this, I'll be creating those slices. So just with my unitary operator, this right, this was try to see how it actually is been created, how the circuit is actually been created. Then I can actually create the whole circuit of it, which is once you understand the one step, the first step, the remaining steps becomes very easy. So that is exactly how the circuit has been built. So we can write this XYZ. So I have taken only a single term, and XYZ can be written as Ry minus pi by 2 tensor product Rx pi by 2 and tensor product iota this way. So I can, if one by one, you will end up having this. Now, once again, once I have this form, and if I now I think all of you have heard about some kind of a C naught gates. Yeah. So C naught gates, if I can write this as a combination of these C naught gates, right? So if you write qubit is 1 and the target qubit is 3, you can create, you can actually multiply these matrices and you can get exactly this form of the ZZZ. Now adding, just like I said, this is not a very straightforward way. Like this is not a very simple also. Once the only way to realize this is once you do the mathematics by hand, then you'll be able to understand how it is exactly coming from this step to this step, right? So as I said, this whole unitary operator can be decomposed into some basis gates like this, and once I have that, I can move forward with the other terms as well. Yeah. So just like I've said, this will be the circuit for the first slice, right? So you will have the RY gate, RX gate, and corresponding C0 gates. Just like I've said, you can see here, the first I am applying the C0 gates, there will be some RY gate, then there will be C0 gates, C0 gates, and correspondingly, the reverse parity that I'm applying here, C0 2 to 3 and C0 1 to 3. And which, so I have just, you see, I have just derived this whole circuit from this, from an unitary operator just by following mathematics, right? So that's the beauty of attacking any problem by just doing maths and logical reasoning, which helped me actually to create this full circuit. So you can see here the XYZ and YIX, the first two terms becomes the circuit, equivalent circuit of this is because becomes like this, and the other two terms equivalent circuit becomes like this. Now this is a continuation. So this continues. Now don't think this two rows. So here is first row, here is second row. The second row will be coming here. So it is a continuation of it, right? So as I've taken the example of a 3-qubit system, so this will be a complete row. Now, if I break those slices into, let's say, k number of k slices, so this will, all the slices would look like. So here, this is the first slice, this is the second slice, this is the third slice. Now what is inside these slices? These circuits, these continuation circuits. So this will continue from here, this, and this will come into a single slice, right? So yeah, and in this way, remember my initial goal was to calculate the final state using a quantum computer. So you see, I just created the equivalent quantum circuit of this operator, the unitary operator. So now I can implement this circuit into a quantum hardware and calculate the final state. Now, where exactly these kind of problems can be relevant? So I think some of you have already heard about some of the practical use cases of a quantum computer, such as till we achieve fault tolerant devices by 2029. Let's say IBM have promised that. Before that, all of your quantum problems, it's either a simulation problem or an optimization problem, right? Once we have that a certain kind of a fault tolerant devices, then only then we will, our QML algorithms, the quantum machine learning algorithms, can be useful and beneficial. Before that, all of our quantum machine learning, whatever quantum machine learning algorithms that are already available there is actually no advantage. So if you see, there is actually no quantum advantage there. It's fact. So before fault tolerance, all of our problems are basically either it's a simulation problem or an optimization problem. So all of our problems we try to somehow manage to direct into these two categories. So through this trauterization algorithm, you'll be able to visualize or able to imagine how this can be relevant, how much this can be relevant in terms of simulation problems. So this actually helped me, this algorithm will actually help me to understand how a quantum system will evolve or how a quantum system will behave after a certain amount of time, which your natural instinct, your hand, your eyes, your nose cannot detect, right? Because a quantum system, you don't can't visualize like a normal system, right? It's a because of its scale, right? So as I said, uh, so I have created the the equivalent quantum circuit of this whole unitary operator, right? So by creating these slices, and what is inside these slices? Inside these slices, there are each of these circuits, right? So now what about the circuit depth? Now we still talk about some 1, 2, 3 gates. Like in Bell state, we also do put some one gate, some other C0 gate, some 1, 2 gates, right? But here you see, it's not only 1, 2 gates. You can see for only one slice, how many gates are here? 1, 2, 3, 4, 5, 6, 7, 8, 9. And 4 times 9 is how much? 36. and for, let's say, I am running it for 500 slices. So how many gates will be there? 500 times 36. So you can imagine how many gates will be there. So it's not a like one gate, two gate, three gate. We're just trying to analyze what is going on, understanding, or no, it's not like that. So we need to analyze how many gates we require or how many depth we have to go to create accurate simulation. So this is kind of an intuitive idea about how it relates to it. So how it once you have the circuit depth, and if you want to reach to a certain simulation accuracy, and how much circuit depth you have to go. So the more slices you go, the better accuracy you will achieve. So which simply suggests that depth is proportional to gate count. Yeah. So this was the kind of the whole workflow of this algorithm, that once you're given the Hamiltonian in the Pauli strings, you can do some Pauli decomposition and mapping, and then you create the trotterized equivalent quantum circuit of that unitary operator, and you run the quantum simulation, which you can run on the quantum hardware, and you finally do the measurement and do the observables and calculate the expectation value of the observables. And here each slice is one small step. If I repeat this for k times, I'll get the full evaluation. Now, what is the output of it? I can calculate the expectation value of those quantities, like any quantity, right? So now, how do I know? How do I know that whatever I have generated is correct or not? So you should have argued with me that, okay, I am saying that this is my circuit, and how am I claiming that this is correct? How do I know that, right? So how do I know that then? I have created a time evolution of 1D potential well. Have you heard about 1D potential well? Anyone? No one? One dimensional potential. It's a classic quantum mechanics problem. You have one guy. Okay. So none of us. Okay. All right. So 1D potential well problem is a classic David J. Griffiths problem. It's a very starting problem in quantum mechanics courses. Um, yeah. So in 1D potential well, if you see the time evolution of that 1D potential well and how the probability distribution moves over time, it exactly looks like this. Now, as I said, I have created the equivalent circuit of this time evolution operator, and if I incorporate that, I am getting the exact same time evolution state. So that's how I get to know that whatever I have generated, whatever my circuit is, it's actually a correct one. It's actually giving me the right result. And that's exactly I feel like you do research. You do some validation, you create your stuff, and you do some validation, and you match with the existing results. If it matches, congratulations, your research work is well defined and it's moving forward. So in QNIVERSE, actually I have implemented this algorithm myself, and so this is the classic 4 steps that you need to perform to uh, uh, to to understand or to do or to implement this algorithm into the QNIVERSE. So first you select the algorithm from the algorithm plate, which is a Suzuki trotterized algorithm, and then you load graph. Now what is the load graph? I'll just explain. But just before that, I'll just try to highlight that how many of you have heard about the quantity named fidelity? So yeah, so fidelity is a quantity which measures how much my quantum state is accurate. So if it is close to 1, that means my quantum state is accurate. If it is close to 0, that means whatever quantum state I do have, it's a very crude approximation. It's a very wrong approximation. So the better the fidelity, better our simulation. And what do you mean by better? Better is close to 1. So fidelity will always lie between 0 to 1. So this will be my, then I'll hit the load graph. And once I have the load graph, then I'll set some parameters. Based on my parameters, I'll able to see how my system is evolving with time. And then finally I'll load it and run it, which will show me the evolved state, which the initial goal that I have started off with, which is nothing but to solve this equation. All right. So I'll just quickly go into the Quniverse to showcase actually how um, it can be done. All right. So just give me a time to log in. All right. So here, if you go into the algorithm palette, and if you go here in the next update, people who have already registered in this platform, in the next update, you will receive this algorithm. But I think for the free users, that algorithm is still not available. So if you hit the load circuit button, here is my Hamiltonian input that I have in the Pauli string. And this is my initial state. And for order one, and if I select, remember those slices that I have talked about, like 50 slices, 1000 slices, 2000 slices. The more I go, the better accuracy I'll receive. I'll reach. And for time, let's say how much? Let's say 5 seconds I want to simulate for. Now, if I hit the fidelity visualization, so I'll have a fidelity visualization understanding about how the fidelity is behaving over a certain time and how it is behaving over the number of the steps. So the more number of steps I go, the closer fidelity goes to 1. So as I said, the more the fidelity close to 1, the better our simulation results are. So yeah, so this is as you can see with the 29 step, I'm reaching out to fidelity close to 1. So if I take 29 size slices, that is good enough for this kind of Hamiltonian to create the equivalent circuit. So once I have that fidelity visualization, based on that, I'll change my input. So I have given the 50 steps, which already includes these 29 steps. So I'll have not a lot of problem with that. So if I just hit the load button, you see, I will redirect to another page, and if I hit the run button, so my Quniverse will run this algorithm for me, and I'll have a unique job ID for this particular job description. And if I just click on it, I'll just refresh it. So it takes a bit of time. So it's still running actually. Yeah, it's done. So you see, this is the exact final state vector that I was supposed to get. And this is the final state vector that I have got using my algorithm. So if you just try to merge this thing together, and the fidelity I'm receiving is uh, 0.99. Now the probability distribution matches quite similar with the exact final state vector that I was supposed to receive with the trotterized simulation version. So that's exactly says that whatever simulation or whatever the circuit that I've run is actually a correct one. So now our team, CDAC, our team itself is working in this platform also to show the circuit. It's still not visible, the circuit. There is, yeah, so there is some internal things that they are doing right now to showcase the circuits also, because because it's not very easy to showcase the circuit as well. Because as I said, the length and the depth of the circuit is very large. So I just gave you just a number, right? 36 times 500. So those number of gates I will have in my circuit. So you can imagine how long, how big, how large my circuit can become. So which is a very challenging thing to show that circuit here in a very short span, a short space. So yeah, with this, I think I have covered the whole trotterization algorithm. So I know this can be a bit challenging to understand in the first place, but if you have this analogy of breaking every complex task into very small, step by step, doable way, you can actually attack any kind of problem, and that's exactly how I have done it. I have implemented this algorithm from scratch. Yes, so with this, I'd like to conclude my presentation, and I'd be open for any kind of questions all of you have. No questions. Wow. You can ask, no problem. No matter how basic it is. No questions? Okay. Yeah. Done, I guess done.
Sir, can you explain the time evolution graph in details?
Yes, yes. Huh?
Time evolution graph.
Time evaluation graph?
Graph.
Of course. Of course. Well, yes. So this is the graph that I think you were specifically referring to. So once I have my Hamiltonian expression, let's say uh, I have it has to be in terms of Pauli gates x, y, z, I, uh, just 0.3 star y, 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 x. So for example, this is my Hamiltonian. This can be very large also. You can put whatever you want, just a very random way. Uh, and I'm choosing my initial state as 0, 0, 0, 0. So the number of the qubit that I'm choosing for the initial state as well as my Hamiltonian should be matching. Why? Because the number of the qubit of the system should be remain consistent throughout our uh, throughout whatever calculations we are doing. So if you choose the initial state of a 3 qubit system, it will throw you some error. So which will say invalid initial state is the syntax error. So which actually says that you have to put your initial state of a 4 qubit system. So here I can select the Suzuki trotter order and then the number of the slices that you want to reach. Let's say I want to reach 100 slices and I want to simulate it for uh, 2 seconds. So if I do the fidelity visualization, so this graph actually speaks about fidelity visualization. Now, as I said, fidelity is a quantity that helps us to understand uh, how much our state is accurate, right? So if the fidelity always be lying between 0 and 1, so if it is close to 1, that means my state is correct, and if it is close to 0, that means my state is the whatever simulation I have done, it's not that correct. So you see, as I said, my Hamiltonian expression was very easy. If I incorporate, let's say 10 seconds, so I'll get the fidelity visualization curve. So it will take a bit of time, I guess, because I have increased the time by a lot. Ah, so it's still coming same. Okay, maybe let me go a bit complex. Y, y, x, I, x, x, y, I, x, y, x, y, x, y, right? Two. So whatever you see in the graph is how over the number of steps, how the fidelity is changing over time, over the number of the steps. Now, the more I increase the number of the steps, the fidelity should go close to 1. So this graph, what actually shows you is how many steps you have to do those trotter slices to reach to the accuracy to a certain level so that your fidelity goes to close to 1. Yeah, you can see here. Uh, okay, I'll just zoom it. Yeah. So you can see here, my fidelity, if I go for only one trotter slice, my fidelity is close to how much? 0.126, right? Which is a very bad. That means my whatever state I have generated, it's completely, you can say completely wrong. So the more I increase the number of the steps, you see when I am reaching to the 9th step, I almost, so if I let's say 5 steps, 5 trotter slice, I'm getting 0.7 fidelity. That means it's getting closer to 1. So which means my simulation is giving me correct results because I am increasing the number of the steps. Now again, I'm going again 7 to 8 to 9 to 12. Once I reach to the 12 number of steps, that means my fidelity is going to 0.9, which is close to 1. That means my simulation results are correct, almost correct, not 100% correct, but 96% correct. Now, if I go more and more and more, you see with the 46, 47, 48, my fidelity will go close to 99.9%. So this graph actually helps you to build an intuition about how many steps you have to actually go to create the accurate simulation. Since it's very difficult to show the whole circuit of that, like the whole circuit of the full unitary operator, because it's a very large circuit. Like, so yeah, when you decompose that into a single qubit gates, yeah. So this graph is actually showcasing how the fidelity is changing with different kind of trotter steps. I hope that answers your question.
Yes, sir. Thank you, sir.
Yeah. Any more questions? No more questions? Okay. Uh, yeah. So, initially when I was preparing my slides, to be honest, I had kind of a very less idea about where exactly all of you are, like in quantum computing. So I saw some of the videos on the YouTube. Someone was explaining Grover's algorithm, and someone was also explaining some Deuce Joshua constant Vazirani. These kind of algorithms they are explaining. So I thought maybe I should explain some complicated algorithms because these people have already covered some of the basic algorithms. So that's the main intention of mine was behind showcasing this totalization algorithm, which I feel a bit hard because it's, to be honest, it's not that straightforward. In fact, I had to put also a lot of effort to understand it and to create it from scratch. So, uh, but I think I should have explained some other simple algorithms also. Maybe that would create a lot of value to all of you. Anyway, but QNIVERSE will help you a lot if you do register. All of you just do register into the QNIVERSE because it's free. Nothing takes uh, from you. So you can just register and explore. If you are interested in quantum algorithms and do quantum research, you can explore all of those algorithms, learn from it, create your own circuit, submit your jobs, and just to get into the space of quantum computing and really be uh, get into a direction of a really good researcher. Yeah. So that's I would like to highlight the fact, and also uh, uh, the hospitality here I have received is really amazing. Thank all of the organizers as well as all the people who have given me this opportunity to speak in front of all of you. In fact, if I would have a little bit of more idea about mostly you are beginner, I would have created some basics stuff also. Um, so, um, so this is the first. Actually, this is the first time I am visiting in Vizag. Yeah, Srikakulam. Not Srikakulam, in Vizag itself. This is the first time I'm coming in this city. And yesterday I got a bit cold as well, some fever also. So I somehow managed to give these two talks, which I think to have a bit of understanding and have a uh, maybe help you in a lot. Okay. So yeah, thank you so much for yeah attending. Yeah, thank you, thank you.
So, what do you think, guys? To me, this was such a fabulous session. It was very informative, and we must thank Mr. Tilok Sadhukhan sir, who walked us through QNIVERSE initially in the morning session, showing us why this platform is powerful for practical quantum computing and learning. We saw how it provides a unified interface and a quantum SDK, and how it lets us run quantum algorithms on GPU processors instead of coding also, and bringing real efficiency to quantum experimentation. So, a very big thank you to Mr. Tilok sir for taking the time to guide us and for sharing such valuable insights. On a personal note, yesterday after traveling, sir actually caught some fever also. But even in that situation, he never backed off, but he took the session in the morning session, and also he have taken his time and efforts to share his knowledge to all of us in the afternoon session also. So let's give him a big round of applause for everything he has did for us. Thank you. Thank you so much, sir. So everybody, I noticed most too many students have lined up for the most exciting part of today, the hackathon, the 48-hour long hackathon from multiple universities. So on behalf of the entire organizing team, I extend a very warm welcome to each and every one of you. Our esteemed faculty members and dedicated participants who valued our guests, especially those who have joined us in person mode from over 30 plus institutions and universities across all over this place. So, your presence here today truly makes this event extra special. So, a big round of applause to you all. And the most exciting hackathon is about to begin in just a few minutes. In the meanwhile, you can take rest or get some fresh air if you want to. But get ready for more knowledge blast just after the few minutes of break. Thank you, guys.